Hi, everybody. This is the lecture video for Chapter 11, where we're going to cover t-tests for two related or paired samples. By the end of this lecture, you will hopefully be able to understand when we would use a repeated measures t-hypothesis test. You'll know how to test the mean difference between two treatment conditions or two measures of a dependent variable using the repeated measures t-statistic. You'll be able to evaluate effect size using the different ways that we've already talked about. And you'll be able to explain briefly the pros and cons of using this type of design, as well as the independent measures design, which we talked about in the last video. So last time, or in the previous video, we talked about Chapter 10, independent samples design. That's also called a between subjects design. This time, a little bit different, we're talking about a related sample design. And so with the independent samples design, you have two samples. They're completely independent of one another. So they have two completely different sets of participants. In a related samples design, you have one set of participants, most often, and you measure a dependent variable with that set of participants more than once, so twice at least, sometimes more. That's why it's also called a repeated measures design. So you might be measuring a dependent variable repeatedly. It's also called a matched subjects, or excuse me, matched sample design is another type of related sample design that I'll talk about a little bit more here in a couple of slides. And it's also called within subjects design. Basically, the independent samples design and the related samples designs are statistically equivalent, but they do use different ends. So with related sample designs or within subjects designs, you're using the same group of participants and you're measuring something twice. So you might have 20 participants and you measure something with them 2 times, and so you only need 20 participants. With an independent samples design, you need 2 groups of participants, right? So you would need 20 participants for one condition, or and then another 20 additional participants for the other condition. So you would need twice as many participants in your sample. I'm going to show you the same table that I showed you in Chapter 10 to kind of refresh your memory on the difference between these two. So a between subjects or independent samples design would have, again, 2 completely separate, different, independent samples. So, you know, with one level of your independent variable, you might have Ross, Chandler, and Phoebe. With another level, you'll have Monica, Joey, and Rachel, right? What we're talking about today are paired samples t-tests or within subjects designs. And for those, you're going to have the same participants and you're going to measure them on the dependent variable more than once. So in this case, Monica, Joey, Rachel, Ross, Chandler, and Phoebe are all going to be measured 2 different times. And this briefly is saying the same thing, right? So repeated measures within subjects designs, what we're talking about today, is when you obtain 2 separate scores for each individual participant in the sample. So you use the same participants in both treatment conditions. Why on earth would you want to do this? When you use a within subjects or repeated measures design, there is no risk of the participants in each treatment group differing significantly from each other, right? So with a between subjects design, because you're using 2 different participants, you can't say, it's harder to say definitively if you see a difference between group 1 and group 2, or level 1 and level 2. Is it because of the treatment that you provided? Or is it because the participants in the second group just happen to do better, right? And so if you use a within subjects design or repeated measures design, you're using the same exact people twice. And so any difference you notice in scores from one treatment or level to the next can only be due to that treatment, right? It can't be due to the difference between Ross and Ross because we measured him twice and he's the same person, right? Uh, so hopefully that's making sense. Okay, some real world examples of when you would want to use this kind of design, a repeated measures or within subject design. Um, if you're going to measure personality traits over time, right, you definitely want to use the same person. Um, and so you can measure a group of people once and then the same group of people again a year later and look at maybe developments or differences in their personality traits. Perhaps a measure of social abilities before and after a social skills intervention. And there's going to be a lot of designs that look like that, right? Where you're measuring some kind of ability or increase or decrease in symptoms before and after some kind of intervention. Um, so the next example is kind of like that: performance on a neuropsychological test after sustaining a concussion. Um, Monitoring treatment outcomes for a client. So maybe you have a client and you're going to measure them when they start therapy, a month later, and then 3 months later, and 6 months later, that kind of thing. Or an example we talked about before, relationship satisfaction before and after positive image pairing. So you could do that research study using either design, right? You could take a group of people and have them look at pictures of their partner when they're also viewing happy stimulus pictures, right? And then a separate group of participants, totally different, um, looking at pictures of their partner with neutral stimuli pictures. Um, if you wanted to do a within subjects or repeated measures design, you could use the same group of participants and test their relationship satisfaction before and after the positive image pairing. So maybe you'd show them pictures of their partner with no images and then test their relationship satisfaction. And then you'd use those same participants and you'd show them pictures of their partner with puppies and balloons and magical happy rainbows, right? And then test their relationship satisfaction. So that would be an example of a paired sample or repeated measures or within subjects design. Okay. Matched subjects design. So this is a little bit different. This is like a variation or a combination of these two basic designs that I've talked about in chapter 10 and with this lecture for chapter 11. With a matched subjects design, you are using two separate samples. So that sounds kind of like the independent samples t-test, right? Um, but each participant in each sample is matched. So like it says on here, each participant in sample 1 is matched 1-to-1 with a participant in sample 2, and matching is conducted on relevant variables. So that could be something like age, gender, socioeconomic status, whatever variable that might be influencing the dependent variable. And so, like I just said, matched subjects is kind of a hybrid design, right? It's not quite independent because the participants in each sample group are matched on some important characteristic. So they're not just random, completely different sets of participants, but they're not quite paired or repeated measures design either, because with a repeated measures design, you'd use the same exact participant, right? And so with matched subject design, you kind of get the best of both worlds. You get the pros of both of these two different types of designs, and you kind of you won't really get the disadvantages of those designs. Let me see, I think there's an example later on in the presentation. Okay, so one real world example might be, what's the difference in number of hours spent at work for employees who have been at a company for less than a year as compared to more than a year? And for this, you might take 30 pairs of coworkers, like one new hire, someone who's been there for less than a year, and one senior employee who's been there for more than a year, and report the number of hours they work each week. What you'd want to do is to match them on, let's say, age. If we think, age is something that also influences the number of hours spent at work each week, or perhaps the job description, right? So someone who's like an administrator versus a C-level executive. And so you'd want to have your pairs matched on whatever important variable might make a difference in the number of hours spent at work. And so one pair might be, between the ages of 20 and 22, and administrator. And so you'd have a new hire that's between the ages of 20 and 22 and an administrator, and a senior employee who's between ages 20 and 22 and an administrator. That way, they're matched on key or important variables, and that in that way they are paired. Hopefully that's making sense. If you can view the lecture in combination with a textbook, and I apologize you can't ask real-time questions, but I didn't want to make these videos synchronous. I wanted you to be able to watch them at any time. So email me your questions, or perhaps I'll try to create a discussion board on D2L where we can ask and answer questions. So let's see here. The most important part. So when you're doing calculations or entering data into SPSS, the most important thing to remember is that you must keep the pairs of scores together. And this is for the matched subjects design, where that's especially important. So there's just something to keep in mind if you're doing SPSS with matched subjects. Let's do an example with this repeated measures t-test design. So let's say you've designed a program to help relieve muscle tension in individuals who suffer from chronic headaches. To test whether your program changes muscle tension, you have 5 participants record their daily headaches over a 2-week period before the program. Then they go through the program, which is 6 weeks long. And for the 2 weeks afterward, you have them again record their daily headaches. And so we're going to essentially be wondering with this research question, does the program change muscle tension? And we are given an alpha level of 0.05. And here's our data. So we have 5 participants. Again, it's the same participants. We're going to measure them twice. This would be an independent samples design if we had 2 different groups of participants. But this is a perfect research question or design for the repeated measures type of study, where you have a treatment and you want to look at before and after the treatment and compare and see whether the treatment is having any effect. Oh, I'm sorry about this slide. I'm not really cutting it off at the bottom there. So in this case, with related samples or repeated measures t-tests, what we are looking at, the key thing to remember here is difference scores. So hypothesis testing is going to begin by stating the hypotheses, right? The null and the alternative hypotheses. And the hypotheses for this kind of design are based on population means for difference scores. And that's notated by this population mean D, mean difference for the population. So again, every individual, we're going to imagine that every individual in the population is measured on the two treatment conditions we're interested in, before and after. And then that a difference is computed for each individual, right? So they're going to have a score or number of headaches before the intervention, and then a number of headaches after the intervention. And we're going to calculate what's the difference, right? So I'm just going to flip back to our data here for a second. Participant number 1 had 10 headaches after the training had 3. We're going to be computing what's the difference, and the difference there would be 7, right? And so all of the data for this kind of design or t-test is looking at difference scores, okay? And for the null hypothesis, we would say that the mean difference for the population is 0. So the null, again, is going to mean that there's no treatment effect, there's no difference, right? The intervention does nothing. And so the number of headaches before and the number of headaches after are going to be equal. Therefore, there would be no difference, right? The difference in headaches before and after will be 0. The alternative hypothesis is that there is a treatment effect, right? And that the mean difference for the population does not equal 0. So again, we would take every individual in the population, we'd measure the number of headaches before, the number of headaches after, we would take the difference in those two numbers, and the alternative hypothesis would say there is going to be a difference, right? There will be some kind of treatment effect. And remember that if your hypothesis is directional, your alternative hypothesis, that is, or the null and the alternative, excuse me, you would use less than or equal to and greater than or equal to, rather than just the mean difference equals 0 or does not equal 0, right? And that should just be review from the other t-tests that we've done. So since the null and alternative or alternate hypotheses are all about difference scores, we need to calculate the differences. So the difference is just score 1 minus score 2. So like I said, 10 minus 3, 7, 9 minus 4 is 5. You're just literally subtracting one score from the other and listing the differences or difference scores over here in this difference column. And then we need to find the average of our difference scores, or mean difference. That's notated by the capital M for the sample mean versus population mean, and then subscript D. And to do that, you're going to take the sum of the differences divided by n. And just note, the difference scores can be negative. That's okay, right? Even when, if you remember way back when we're calculating sum of squares, squaring can always get rid of the differences. So the average difference is 4 when you calculate it out using this formula, the sum of the differences divided by n. So we get 20 divided by 5 equals 4. We also need to calculate standard error for our different scores. We're going to use that in the formula coming up. So we'll just go ahead and calculate sum of squares here now. So you'll see I've listed sum of squares equals 18. Here's the formula for sum of squares, in case you forgot. It'll be on a later slide again as well. So be careful if you're calculating sum of squares in a practice problem or on an exam. Be careful where these parentheses are, right? So here, you're going to take the differences squared and then add them up. Over here, because of the parentheses, you're going to use the sum of differences, which we've calculated to be 20, and just square that, okay? So review or ask me if you have questions about this, but remember that the parentheses make a difference here. Okay, step 2 in hypothesis testing, always set the decision criteria. That has not changed with this particular hypothesis testing or t-test. We were already given alpha as 0.05. We're going to do a two-tailed test to see whether our treatment has an effect. We didn't say whether it would decrease or increase headaches. We just said it's going to do something to the number of headaches. What's our degrees of freedom? So our sample size n is based on the number of pairs. So n equals 5. So with an independent samples t-test, you would have 2 separate groups, right? And the sample size may or may not be equal from one group to the next. With this type of t-test, the paired samples or repeated measures t-test, you just have one group of participants, right? And they're being measured twice, but it's just one group of participants. So in this case, we have 5 participants being measured 2 different times, n is 5. It's pretty straightforward. And therefore, our degrees of freedom is 4. When you look that up in the T table, you can see that the T critical value is plus or minus 2.776. And then we will go on to step 3 of hypothesis testing. So we're going to use the mean difference as the sample mean. And remember, before it was just the mean, right? And instead of comparing a sample mean to a population mean, we are setting the mean difference for the population at 0, based on our null hypothesis, right? So just to refresh or remind you, here in this kind of t-test, everything is about the difference scores, right? And our null hypothesis said that the mean difference would be 0. And so we're going to base this T formula, this part of the T formula, the mean difference for the population, on the null hypothesis. And doing that means that the mean difference for the population is 0. And so our T formula really just comes down to the mean difference of the sample over standard error. And how do we calculate that standard error? This is saying the standard error of the mean difference. So just take a second and really make sure you understand what this formula is talking about, right? If we have a sampling distribution of the mean difference, what we want in the denominator of our T formula is the standard error of that sampling distribution, which is the mean difference. So standard error of difference scores. Remember, we are interested in comparing our obtained mean difference to the expected population of difference scores if the null is true. We can calculate that very similarly to how we calculated standard error for the basic one sample t-test, the very first t-test that we talked about. But now the difference here is that the standard error, or S squared, is a variance of difference scores. Okay. So remember our variance equation, hopefully. We will use that variance equation to calculate our standard error or variance for the difference scores, and then plug it into the formula for standard error. So remember, we can calculate sum of squares, and we, on the previous slide, or 1 or 2 slides ago, we calculated it to be 18. So here is our formula for variance. Variance is the sum of squares over n minus 1, or sum of squares over degrees of freedom, right? Degrees of freedom is n minus 1. And then the standard deviation of this mean difference sampling distribution will be square root of variance, S squared, over n. So doing the math and plugging in numbers for the example that we're working with, Variance here is the sum of squares over degrees of freedom, and you can calculate sum of squares with the formula I had on the previous slide, and I told you that it comes out to 18, and our degrees of freedom is n minus 1, which is 4, and so we get a variance of 4.5. We can plug that into the standard error formula. Standard error is just the standard deviation of this particular sampling distribution. And again, this particular sampling distribution is the mean, or the mean differences, right? It's a sampling distribution of average differences. And so we'll take the square root of our variance, calculated over here to be 4.5. We'll divide that by n, or 5, and we get a standard error figure of 0.95. Now we have everything that we need to compute the test statistic, to calculate T, or T obtained. And so here is the formula for T in a paired samples or repeated measures research design. T equals 4, so the mean difference for our sample, which we've computed based on the data on the previous slide, minus 0, again, this population mean difference is based on the null hypothesis. And the null hypothesis would say that the population mean difference is going to be 0. So that's where that 0 is coming from. And then divided by the standard error that we just computed on the previous slide. And you get a T of 4.21. So remember, our null hypothesis was that the population mean difference would equal 0, and our alternate hypothesis was that the population mean difference would not equal 0. We already looked up our T critical, would be plus or minus 2.776. We've now got our T obtained, 4.21. And now moving on to our last step, what is our decision? So here on this graph, I've tried to show where T critical and where T obtained is. And we definitely are going to reject the null, right? We have sufficient evidence to conclude that the headache treatment is effective, that there is some kind of effect, right? And here's how you would report it. You would state that, and then you'd say T with 4 degrees of freedom equals 4.21, and that's with a p-value that's less than 0.05. And then you can look at what was the average difference. It was 4. So you could also say it looks like people had an average of 4 fewer daily headaches after the treatment. Now let's look at effect sizes and confidence intervals for a related samples design. Cohen's d, this should all be review, right? D equals the mean difference over standard deviation. Percentage of variance explained, or R squared, is what the abbreviation is for percentage of variance explained, is T squared over T squared plus degrees of freedom. And then to compute confidence intervals, you're going to take the mean difference plus or minus T critical times standard error. So same formulas here for our example. So we've got a Cohen's d of 1.89 when you do the calculations. That means that the treatment brought headaches down by 1.89 standard deviations, and that's quite large. For variability, for percentage of variability explained, when you plug the numbers in, you get R squared is equal to 0.816. And if you were going to interpret what does that mean in English, that means that 81.6% of the variability in headache frequencies can be explained by the treatment. And just as you'd expect, that's also a very large effect. It would be quite unusual, and I'm not going to go as far as to say impossible, but definitely quite unusual for Cohen's d and the percentage of variability explained to be different. So if Cohen's d effect size is small, you're not going to get an R squared that is large, right? They should match. And then computing a confidence interval at 0.95 or 95% confidence interval. Here you're going to get 1.36 to 6.64. And again, the in English interpretation of that is that there's a 95% probability that the true population mean difference is in this interval, in the interval between 1.36 and 6.64. Notice that our null hypothesis value of 0 is not in that interval, right? And again, kind of the rule there is if 0, your null hypothesis value, is in the interval, then you probably should not be rejecting the null, right? And if it is, or I'm sorry, if the 0 is not in the interval, then you should reject the null. And that's what we've already decided based on our t-test or hypothesis testing. So computing a confidence interval, again, is kind of a check on your hypothesis testing procedure. Okay. So this is something that we would do in class if we were meeting in person and we had the whiteboard and I could ask you guys to tell me what we would do here. I'm not going to do it on a video recording, but this is a great practice and a pretty straightforward practice where, again, you're going to go through all of these steps that we just did for our example. Just a moment. Okay. Sorry, guys, had to pause that for a second and I'm back now. By the way, it is now after midnight as I'm recording this, and it's my birthday. Fun trivia fact that will probably appear on the quiz question for those of you looking for the extra credit. So back to this practice problem. You're going to start by computing the mean difference. So you're going to sum the difference, divide by n. Here's a column where you could calculate the differences, add them together, divide by n, compute sum of squares. Again, here's your sum of squares formula. And then you're going to compute variance for the different scores and standard error, just like we did in the previous problem. Okay, if we were in person in the lecture, we would do responses on our phone, but maybe you can kind of do it on your own, following along with the video here. For which of the following would a repeated measures study be appropriate? A group of twins tested for IQ, comparing boys and girls' strength at age 3. C, evaluating the difference in self-esteem between athletes and non-athletes. And D, students' knowledge is tested in September and December. I'll give you a little moment here to see which one you'd choose. And the answer is D, students' knowledge in September and December. Just keep in mind when you have a group of participants and you're measuring scores twice, that's where you would be using a paired samples or repeated measures design, right? So you're repeating the measure of something, in this case, students' knowledge, twice, September and December. In all of those other examples, you had 2 different sets of participants, right? Boys and girls, athletes and non-athletes, twin A and twin B, right? So those would not be repeated measures because repeated measures uses the same exact group of participants twice. All right, for which of the following would a matched subjects study be appropriate? And remember that matched subjects is the sort of hybrid, right? Where you're not using the exact same participants twice, but you're matching the pairs of participants in some important way. So they're not entirely different, but they're not the same. And so you have the same choices as in the previous question. Which one do you think would be most appropriate for a matched subjects study? And the answer is A, a group of twins, right? So presumably the twins should be similar in most other ways, right? Gender, age, other variables that might be influential on the dependent variable, but they're not literally the same person being measured twice. Okay, true or false, a matched sample study requires 20 participants to obtain 20 scores in each of the conditions being compared. So think carefully here. You have 20 participants to obtain 20 scores in each of the conditions being compared. So let's say you've got two conditions and 20 participants and you want 20 scores. It's a matched sample study. So that's the important thing to know, matched samples. The answer is false, right? So if this was a repeated measures design, then you would only need 20 participants and you could get 20 scores in one condition and 20 scores in the second condition. But since it's a matched samples study, you would need 20 additional participants, right? And you would want to match each pair on some important variable, but you'd have 20 participants for the first treatment condition and 20 additional matched participants in the second treatment condition. So back to our lecture, a few factors that influence the outcome of repeated measures hypothesis testing. These are really similar to other t-test factors that we've talked about. The size of the sample mean difference, right? So the larger the mean difference is, the larger the numerator is in our t-test statistic, and so the larger t you get. And as your t gets larger, you're more and more likely to reject the null. So if the mean difference is pretty large, that definitely influences the outcome of the hypothesis test, meaning whether you will reject or not reject the null hypothesis. Another factor that influences the outcome of a hypothesis test is the sample size. Of course, the larger n is better, right? Larger n is going to give you smaller standard error, which is going to give you a larger t. Sample variance. So the smaller the sample variance, the smaller the standard error, and again, the larger t-value. I remember we've talked about before how variance can obscure differences in a t or hypothesis testing scenario. And so large sample size is good, smaller variance is good, and in this case, the large mean difference or sample mean difference is going to be important. Okay, advantages and disadvantages of this kind of research design. And you would learn a lot more about this in far greater detail in a research methods course. So I'm just going to briefly go over these. Some advantages of a repeated measures design. So repeated measures require fewer participants, right? You use the same group of participants over two different conditions or levels of the independent variable, so you don't need as many participants, and that's kind of nice. You're able to study changes over time. Remember, repeated measures is perfect for looking at whether a particular therapy is working or a treatment is working or something, again, changes over time. Repeated measures also reduces or eliminates the influence of individual differences. So in an independent samples t-test, you would have differences between participants in group 1 and participants in group 2. And of course, repeated measures, since you're using the same participants and measuring them twice, you get rid of all of those individual differences that could affect your results or your outcome. Okay, and then substantially less variability in scores for a repeated measures test. And again, less variability is better in terms of getting a larger T and being able to accurately or correctly reject the null hypothesis. Okay. Some disadvantages of repeated measures design. Factors besides treatment may cause a participant's score to change during the time between measurements, right? Of course. So you're measuring, whether or not a particular treatment for depression works, let's say a particular kind of therapy, and you measure in January and you measure in June, and repeated measures is a good design for that kind of study, but there might be all sorts of other things going on that would affect someone's depression score, right? Like the weather, the change of seasons, when you're measuring IQ, maybe additional education changes that. So there's all sorts of things that could go on in a person's life between two different time measurements that could affect results. And then another important disadvantage is that participation in the treatment might influence the score in the second treatment. This is called order effects or practice effects. So there's usually workarounds and ways to avoid this, but it's something to really be aware of and possibly try to correct for. So if you give someone an IQ test and then a week later you give them the same IQ test, they might catch on or figure out some of the answers to the questions. And so again, there are workarounds. Usually there's two different versions of an IQ test. But it's definitely something to keep in mind that someone could get used to the measure or they could become practiced at a measure or a test since they're taking it twice. Okay, and just like the other t-tests that we've talked about so far, there are some assumptions of the related samples t-test. And it's important to check these assumptions before conducting the t-test. So first, observations within each treatment condition must be independent, meaning that within each treatment or level, the scores obtained from different individuals should be independent of one another. And that should be just kind of common sense when you think about a research design or statistics. And the second is that the population distribution of difference scores must be normally distributed. And that's something you want to check, but like the slide says, it's not typically a serious concern unless the sample size is quite small. So if you have a sample size of greater than 30, you're usually fine. The population will be distributed normally enough that you're not violating this assumption and you can interpret your results. Okay, some more learning checks. True or false? Compared to independent measures designs, repeated measures studies reduce variance by removing individual differences. I'll just give you a minute there to think about that. Do repeated measures studies reduce variance? And that is true, right? You're using the same subjects in both treatments. And so you are removing the variance of individual differences, right? If you think back about our table with our friends, right? If you have Ross in treatment one, level 1, and Monica in level 2, you're going to get some individual difference variations, right? If Monica herself and Ross himself are taking both levels, then there's no individual difference across those treatment levels. True or false, the repeated measures T statistic can be used with either a repeated measures or a matched subjects design. And I'm glad I included this question because I don't think I mentioned this in talking about a matched subjects design. And the answer is yes, true. Both of these related samples tests reduce individual difference across treatments. So we would use this particular t-test, this t-test formula for both a repeated measures design, which uses the exact same participants, measuring twice, right? Repeated measure. And we could also use it with a matched subjects design. And again, that matched subjects design is a hybrid design where you're going to match each pair of participants, so it won't be the same exact individual, but they will be matched on important characteristics. So you can sort of treat it as if it is the same exact individual. And that's why you would use the same t-test, the same statistical procedure. Okay, so I'm going to post some practice problems on D2L, just like I have in the past for other chapters. When you're doing those, you want to keep in mind hypothesis testing is the same four-step process as with other tests we have done so far. So you're going to state the hypotheses and select or be given the alpha level. You want to find the t critical value. You want to calculate your t obtained or your t-test statistic, and then make a decision and state the three-part conclusion. Okay, that's the end of our paired samples, repeated measures, chapter 11 lecture. Again, if you have questions, send me an email. And I perhaps will look into starting a discussion board where we can kind of all ask questions and answer. And we'll be in touch later this week. Good luck to everyone.